Right, in this lesson, we shall focus on the chemistry, grade 12 physical sciences, with a specific focus on chemical equilibrium or chemical equilibria. We shall spend a significant amount of time solving past exam questions and other questions which will actually obviously sort of emanate as questions of great interest to us. And we are most certainly getting started. And we shall solve tons and tons of questions together. Right, as part of so now you need to make sure that you have access to your document, please, because obviously this particular discussion is a discussion that is sort of structured according to your document. And it is very important that you have access to your document so that you're able to actually follow exactly when you do these questions. Okay, in particular, we're looking at this first question that appears on the screen. And this first question that appears on the screen is a very interesting question. And it is actually a question that has been extracted from your document. Right. And if this question has been extracted from your document, we're taking a look at it very, very carefully together. We're seeing exactly how this question needs to be done. And we actually will do this together. The next question, for instance, is going to be exactly the KC calculation that addresses the KC calculation of your question. Right. And also we have with us another question that is from your document, or at least this question addresses the 6.4 part. Right. It is possibly very similar in the beginning, obviously, but the 6.4 part is what you're going to address. Next, we have another question that is also from your document. And this question from your document appears to be a sort of repeat question that sort of appeared in your, right, that sort of appeared in one of our discussions. But we shall have a chance to do this question as well. Next, we have, okay, I'm reviewing the rest of these questions. We have this question as well. There's an extension, but now this one is having the 6.2, 6.3, up to 6.5 parts. We also have the next one, 2017. Okay. The next, 2018. So the next 6.1, 6.2. Okay, then we have exactly this question that was discussed earlier, and then we have this one from the KZN province, and then we have the Winelands question, and we have a couple of those questions and a lot of the questions like this one here. We have this one from a document. We have exactly this one also from your question. Okay, good. So awesome. So we shall do these questions in a random fashion. So because obviously they're part of the document, what I will do is I'll do the questions in a random manner. For instance, we shall start by looking at, I feel, most of the provincial exams rather than national exams. And then we shall also do the provincial of KwaZulu and the rest of it. Okay, right. We shall start by looking at the very last question from November 2014 paper. Right, so shall look first at the November 2014 paper as part of your document. And the November 2014 paper is actually the one at the very end of your document.
Oh, okay. The syringe.
Yeah, the syringe, the one with the syringes. Okay, good. Right, we shall look at the question with the syringes, and we shall solve that one, which is this one here. And then we shall actually obviously do the rest of them, but yeah, we shall be doing them bit by bit. Okay, question by question. But we're starting from the national exams first. That is the plan. And then we can do the KwaZulu and the others because from the winelands and other provinces. Okay, good. Right, so this is the question we shall focus on first. And this question first appeared in November 2014. And what is the question? We read through the question together. A certain amount of nitrogen dioxide gas, NO2, is sealed in a gas syringe at 25 degrees Celsius when equilibrium is reached. Okay, so this is the case, and it is actually sealed in a gas syringe at our room temperature, 25 degrees Celsius when equilibrium is reached. Right, the volume occupied by the reaction mixture in the gas syringe is 80 cubic centimeters. Right, so we have exactly that. The volume occupied by the reaction mixture in the gas syringe is that. Okay, right, the balanced chemical equation for the reaction taking place, it's this one here. We really can see what is happening here. This is a reaction in chemical equilibrium. Right, we can see that the NO2 gas gets converted to N2O4 through this equilibrium process. Now, we have NO2 dark brown, changes to colorless. Colorless becomes dark brown. Define the term chemical equilibrium. Right, so let us look at the first question first. 6.1. What is the meaning of the term chemical equilibrium? Right, so we discussed these together. So chemical equilibrium refers to the stage, right? It refers to the stage in a chemical reaction, right? The stage in a chemical, right? So the stage in a chemical reaction, okay, right? When the rate of the forward, right, of the forward, right, the rate of the forward reaction, right, reaction equals the rate, right, equals the rate of the reverse reaction. Okay, let us take a look at these and read and make sure we understand this. I know this is pretty straightforward. Okay, we know chemical equilibrium. Right, what is the meaning of the term? So we're defining the term chemical equilibrium for 2 marks, the stage in a chemical reaction when the rate of the forward reaction equals the rate of the reverse reaction. So chemical equilibrium has to do with what? With rates, right? So we have the rate of the forward, that equals the rate of the reverse. So when the rate of the forward reaction equals the rate of the reverse reaction, then we say we have chemical equilibrium. Chemical equilibrium, right? And in the next question, we answering the question, at equilibrium, the concentration of NO2 gas is 0.2 moles per cubic decimeters. The equilibrium constant for the reaction is 171. This is the equilibrium constant. It's 171. It is the Kc, which is 171 at the temperature of 25 degrees Celsius. Calculate the initial number of moles of NO2 gas placed in the gas syringe. We focus on 6.2. Right, so let's look at that one. At this point, there are a couple of things that are very, very important to us. But what are the important things? But what do we need? We need to calculate the initial number of moles here. And to calculate the initial number of moles, what do we do precisely at this point? A couple of things that remain very important. What is the Kc expression for this particular reaction? The Kc expression for this is the concentration of the products, which is N2O4, divided by the concentration of the reactants, which is actually NO2, squared. That way. And what else have we been told? The equilibrium concentration. At equilibrium, we have the concentration of NO2. So, and that is what we put in the KC because we have equilibrium constant, and we have exactly that. Okay. Now, we're going to obviously draw the table here, but we take note of the fact that there are key things. Once they give you the concentration at equilibrium, you know that it is at the equilibrium constant of 171, which means that we have exactly 171, right? So 171 is the KC, which is actually equal to N2O4. We divide that by the concentration of NO2, and we put it here, so which is actually 0.2 squared, like so. And so what is this? From this particular equation, we're able to achieve that N2O4 concentration of this is actually the product of 171 together with 0.2 squared, right? Meaning now this particular concentration of N2O4, right, is exactly the following. So now we're going to do the calculation here. Okay, so we have our calculator ready. We're going to launch our calculator. Let's see now the task bar, and we have a calculator this. Okay, if this is our calculator, we have exactly 171, and we multiply that by the 0.2, and as a result, this is all squared. And we have the result, and we put it as a decimal, and therefore this is exactly 6.84. 6.84. So at this point, then we have 6.84. Concentration is measured in moles per decimeter cubed, right? So which is actually moles per decimeter cubed, and this is nothing other than the concentration of N2O4. Now, we then continue to say we have obviously not yet answered the question in full because the examiner is interested in the number of moles of NO2, okay, right, in the gas syringe. So now, how do we therefore get the number of moles of NO2 in the gas syringe? We proceed as follows there. The couple of things you need to do, so you're going to use the RISE technique. Right, so using the RISE technique, first things first, we focus on the reaction. Right, what is the reaction? Right, we know that the reaction at this point is actually exactly NO2. And it is exactly N2O4. Okay, so we write that one down. So we have N2O4 as a gas. Moreover, what then are we able to achieve? We actually then have the initial quantity, right? So we have the initial quantity, and this initial quantity is in what? The initial quantity is in mole. And we have the change. We have the change in mole. And then we have the quantity. We have the quantity at equilibrium. We have the quantity at equilibrium. Okay, let us draw a couple of lines here. Right, so we're drawing a table. We're drawing a table so that, okay, we have the change in mole, and we have this quantity at equilibrium, and then we also have what? We also have the equilibrium concentration. Right, so you're going to put here the equilibrium concentration. We have the equilibrium concentration. Right, so if we have the equilibrium concentration, then what do we have here? Right, so let us complete this table. So to complete this table, right, what is the initial quantity, right, in moles? Remember that a certain amount of nitrogen dioxide gas is sealed in a gas syringe at 25 degrees Celsius, right? So we're starting with what? We're starting with a certain amount of NO2. So we have this one we're starting with initially, right? So we're starting with NO2. When equilibrium is reached, the volume occupied by the reaction mixture in the gas is this. So, right, we're given the volume, right, that is occupied by the reaction mixture in the gas syringe. The balance chemical equation for the reaction taking place is exactly this one here. Right, so what then do we need to do here? Right, a couple of things, therefore, remain very, very important. We need to take note of the fact that we need the initial number of moles. Right, so the initial number of moles of NO2. How actually can we be in a position to do that? Because we've been given the concentration C. Right, so we're given the concentration of NO2, and we can always say that. So let's just take note of that. So you're given the concentration of NO2. So if you're given the concentration of NO2, which is actually 0.2, 0.2 moles per decimeter cubed. Right, and what else? We're given also the volume. Right, we're given also the volume. What is then the volume here? But now remember that this NO2 concentration that is given, it's at equilibrium, right? So if it is actually exactly at equilibrium, let's put it here. So equilibrium concentration of NO2 is 0.2. Right. Now, what is the equilibrium concentration of N2O4? It is 6.84. Okay, good. So in other words, we have put these things here at equilibrium, but it's an interesting question. We need to work our way backwards because we need the initial things. We need to actually fill this up, and then now the question becomes, what is then the change here at this point? Right. So if you therefore are able to perform the calculation and say,
How did you get 6.84?
okay, that's a good question. How did you get if we multiply 171 by 0.2 squared, okay, from the KC equation, right?
So you use the KC. You use the KC first.
Yes, we use the KC value of 171, right? And having used the KC value of 171, we're able to get the 6.84, which is what? Which is everything is at equilibrium here. So we're starting with 0.2 at equilibrium, and we have the concentration of the N2O4 also that occurs at equilibrium. Okay, right, we good. Next, the couple of things that we need to take into account. Right, so what then are we going to have with we're going to deal with what we call the equilibrium number of moles. Right, for example, what will the number of moles at equilibrium? Working our way backwards, so the quantity at equilibrium. Because we already have this, right? So now we're going to use our usual old friends, the formulas we know for the number of moles, like concentration, because we have concentrations here, we need number of moles. So concentration is number of moles on volume, right? And so let's think about what we actually need to have here. So if we know very well, yes, we know very well that this is the volume. So we need the number of moles. So we're going to do this and say, for instance, the number of moles of NO2 at equilibrium. Okay, because yeah, they gave us these things at equilibrium. So work our way backwards. as part of what you need to do. And so now we're going to use this formula. This formula is number of moles is concentration by volume for NO2. What is the concentration? Okay, for NO2, the concentration is 0.2, right? For NO2, it is actually 0.2. What is the volume? The volume is exactly this one, but you divide it by 1,000. So we can write 80 times 10 to the minus 3, because you're converting from cubic centimeters to the cubic decimeters. Right, let us use our calculator here to do this one. Task bar, yes. Okay, so, okay, let's calculate this. So this is going to be exactly 0.2 times 80 times 10 to the negative power to the negative 3. Okay, like this. Okay, is the button. So we have 0.016, and this is the number of moles at equilibrium for NO2, 0.016, so 0.016. Right, 0.016. Okay, number of moles of NO2, 0.016. Okay, so we're filling in, we are just completing this table here. Now, we have here also this, N2O4. We need its number of moles. So the number of moles of N2O4 is CV. Concentration for N2O4 is 6.84, and the volume, right? Divide by 1,000, which is actually 80. By 10 to the minus 3 dividing by 1,000. And we're able to get now this. Okay, we're working backwards from equilibrium to the beginning. So now, this one I will just calculate it here so that we're able to do this one. And then we'll be right back. Now we're going to take the 6.84, yeah? 6.84, and we multiply by the 80. We multiply by 10 to the negative 3. In other words, we divide by 1,000. And what is all this stuff here? Okay, it is 0.5472. Check that part. So 0.5472. Well, we're dealing with like 2 decimal places, so we can round it off to 0.55. Okay, we good? So it is 0.55 mole. So it is actually 0.55 moles there. Okay, right. So now we have the quantity at equilibrium, we have the equilibrium concentration with the equilibrium number of moles. Now the question becomes, right, let's deal with a couple of changes here, like with the N2O4. With the N2O4, right? Remember that when we started in the beginning, we had 0 here. We had 0 because we started with NO2 because a certain amount of nitrogen dioxide is sealed in a gas syringe. Okay, we start with NO2, so there was no N2O4, so there was 0 number of moles of N2O4. But now we're going to use the mole ratios. And using the mole ratios, so we're going to then say, okay, if this is the quantity at equilibrium, then here we must have had 0.55 as the change, right? So now if it is 0.55 as the change using the mole ratios, what will this one be? So this one is going to be exactly the change here, which would be the NO2 reacted. So it's going to be 2 times 0.55. Okay, so because of the ratio 2:1 ratio, we have the 2:1 ratio, so it's going to be 2 by that. and now let us do that one. And we use our calculator to launch, to do the calculation. Okay, so we're gonna do what? We're gonna do 2 by 0.55. Right, so this one here is it's 1,1. 1,1. So now this is actually can run off to say 1,1, 1,1 approximately, or y'all. Right, so we have exactly, just say approximately 1,1. Right, so obviously if it's 1,1, then we work backwards and we want to deal with the initial. So in other words, there was an initial amount here, and the initial amount was an amount X. There was an initial amount which was an amount X, and then if you subtract this particular substance from it, you get this one here, and then we're good. We're good. Okay, so yeah, we can get the initial now, we can get the X. And to get the X, we want, we're gonna say, if you're dealing with the initial, right? Let's start chop a little bit. Right, we started.
Don't you say minus x?
Please come again.
Don't you say minus x?
Yes, we do. We say minus. We say minus. So in other words, what are we going to have here? We can say it is exactly X initial, but this one was reduced because it's the initial this. So, okay, this you can say minus, the change. And then this one you can put plus. You know, sometimes it helps. Okay, because now the change, at the level of the change, that's where you can put the signs, you know, but obviously we have the initial there. So we're starting with X, and then the change is minus because it's what we started with, and then it's undergoing reduction. So we have minus 1,1, which must equal the quantity at equilibrium, which is 0,016. Right. Now we can do better. Please allow me just for one split second. Somebody says it's a split second. Okay, there's a split second we can use to do this. Okay, to get a very accurate reading here, right, which is the 6.84 multiplied by 80. 80 times 10 to minus 3. Okay, we wrote this one. 5472. Okay, yeah, we rounded that off to that. But please allow me to write a more accurate result here, which is 0,5472. Right. So the number of moles of N2O4, 0,5472. Okay, that's what we have. So, but it's going to help us to get a more accurate answer here. So if we come here, then we're going to say, okay, we started at equilibrium. So the examiners are always counting people. So it depends on where everything starts. So now they have a tendency of starting either you started initially or equilibrium, or yeah, or sometimes they can give you the changes. Okay, the changes are not very usual, but yeah, it can happen. Now, I want to put an accurate result here. 0,5472 times 2. Okay, it's going to give us a more accurate answer. You'll see why, because obviously sometimes if you round off, we round off, but we need to keep the accurate answers at the back of our minds. So then we have 2 times 0.5472. 2 times 0.5472. Okay, it's exactly this one. So, which means this one is quite a very exact result, which is 1,0944. Okay, so that's what you're going to have. Right, so this one here is going to be exactly what? This one here. It's 1,0944 moles. That's what we have here. We can even write that one down. Yeah, but yeah, it's okay. And then when we have that, I'm writing that so that you can come here and use it here. And then now we're gonna say the change, we put plus minus. You know, we can minus because we start with this, then it undergoes reduction. This one increases. Okay, right. So now we then say minus this guy here. So it's x minus whatever. Then we have equilibrium. What is left? We have what is left. Okay. So now it is minus 1,09 for 4, which is 0,016. Okay, so we add the answer. Okay, so we add the answer. All right, so let us, okay, I'm gonna move the calculator and put it towards the right. And put it towards the right. So now let us use the calculator here to get the answer. Okay. Maybe not the time yet. Okay, that's fine. So we have 0,016, then we add 1,0944. Okay, we move this one to the other side. We move the 1,0944. And then it's going to give us, yeah, now we can launch the calculator and just do the addition of the decimals to make sure we get the correct answers. Okay, right. With that mentioned, what is this? So this is precisely 0.016, right? We add to that 1.09 44, and then we have the result, and the result is this one, which is 1.1104. 1.1104. 1.1104. And this is the answer. And then now we can come here and say, Mr. Examiner, what do we want? We want the initial. Okay, let's start a little bit from the margin and write a bit more. Right, what do we want, Mr. Examiner? We need the initial. We need the initial number of moles of NO2 gas. And this one here, we can see it is 0,016 plus 1,0944, which obviously is approximately 1.11 moles. Okay, so yeah, what is the X? It's 1,11 mole. Okay, you see, normally we put X for the changes, but this time around, we put X somewhere else, but in just the beginning. So it's 1 mole. So there it is. So this here is the number of moles initially that was present in the gas syringe or in the syringe. Okay, it's a gas syringe because we have gases here. There is NO2 gas that was put in the gas syringe, and we have that. So we found these. How many marks was it? 8. Okay, this was a national exam. So yeah, national exams are better accurate because they are very much moderated. So yeah, the marks were heavy because the calculations were also quite a lot. You know, any question now or any input, any suggestion, right, anything we need to change, anything we need to add? Or
No.
too obvious. Too obvious. Okay, that's fine now. Let's move to the next one. To the next question that appeared in the same paper. Okay, we're gonna see a couple of things. Right. So let's move to the next thing. Like we're gonna see this one. Yeah. Okay, now we're dealing with the syringes, and these syringes are a lot. Let's deal with them. So at this point, we are thinking hard, thinking extra hard. A certain amount of nitrogen dioxide gas is sealed in a gas syringe at 25 degrees. So yeah, when this happens, okay, the rest is it's something we've read before. And we're able to see that this kind of a reaction is exothermic because the heat of reaction, delta H, is less than 0, meaning the heat of reaction is negative. Okay, we're able to see that. And now the examiner proceeds to then say the diagram below shows the reaction mixture in the gas syringe after equilibrium is established. Okay, after equilibrium is established. So Right. So now the pressure is now increased by decreasing the volume of the gas syringe. Right. So if this is the case, all right, of the gas syringe at constant temperature, as illustrated in the diagram below. All right, we're good. Then what is the examiner asking us? Immediately after increasing the pressure. Okay. Because the pressure is now increased. Somebody is increasing the pressure. Right. So when the pressure is increased, by how is it increased? By just decreasing the volume. Because the syringe was here, they push it further in, and then it is like this. So obviously the volume here is now smaller, yet the pressure has therefore increased. Okay, let's see what the examiner asked the students in the 2014 November exam. Right, immediately after increasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. Okay, so it is appearing darker than before. Whatever is dark brown is NO2 that is dark brown, and N2O4 is colorless. Give a reason for this observation. Give a reason for this observation. Right. So, okay, yeah, let's first answer that particular part of the question. Then we shall look at the fact that after a while, a new equilibrium is established, as illustrated below. The color of the reaction mixture in the gas syringe now appears lighter than the initial mixture. Okay, we're good, yeah. So we're going to do these in a couple of stages. Let's look at 6.3.1. Give a reason for this observation. Why is it that when this gas syringe, now somebody presses this plunger, when they presses this plunger inside the syringe, suddenly it appears darker than before? The mixture appears darker than before. Why? Right, sir. If the pressure is increased in 6.3.1, we make the first observation. So concentration of the gases increases. Concentration of the gases. Concentration of the gases. Right, you can say the concentration increases, which is the concentration of the gases. Right. And how many marks was this? Just one, so you don't need a lot of things. Right, you can say concentration of the gases increases, or you can actually say that, you can say alternatively molecules. Okay, the gas molecules become more condensed. Right, if you want to say they're more condensed or move closer to each other. Okay, yeah, so what is happening here is the fact that the plunger was here. Somebody pushed it further in. When they push the plunger further in, now you have a smaller volume. Okay, the volume is much smaller. When the volume is much smaller, then it means the concentration increases. Right, so whenever the concentration then increases, why? Because the molecules become closer to each other. They move closer to each other. And because now, when you then say the volume decreases. So in other words, you see the fact that the volume becomes smaller, the space becomes smaller, so the volume decreases. When the volume decreases, what does it mean? Well, it implies, therefore, that we expect that the concentration does what? The concentration increases. So yeah, so now, if you decrease the volume, then we expect that the concentration decreases by the general inverse relationship. Right, inverse proportionality, or what do you call inverse relationship or inverse proportionality? Right, inverse relationship. Okay, so yeah, that is exactly the reason, using the fact that now concentration is number of moles on volume. Generally, if we expect under normal conditions, we are saying the volume does what? We're saying the volume decreases. So we expect that the concentration will, in this case, go up. Okay, so that is the reason for that. Let's look at the next question. Right, in the next point, we've put a lot of these. Okay, this slide, I've put lots of these, like here. Okay, I've put a lot of the syringes now. They're like too many syringes, because in the previous slide we put right, okay, they're a little bit more, but we put 6.3.2 as well as a question. Now in 6.3.2, they're saying after a while a new equilibrium is established as illustrated below. The color of the reaction mixture, okay, after a while. So somebody pressed it and then allowed these to sit, to stay like this. After a while, a new equilibrium is established as illustrated below. The color of the reaction mixture in the gas syringe now appears lighter. Okay, it was dark, but now it's lighter than the initial color. Use the Chatelier's principle to explain the color change observed in this syringe. Use the Chatelier's principle to explain the color change. How did the color change by itself? Because now the color was dark, and then somebody allows it to stay or to sit there, and they just look at the syringe, and then suddenly the color is lighter, but it was darker before. Let's use the Chatellier's principle to explain. The Chatellier's principle to explain what happened. Why is this color just changing from darker to lighter? Why? The first point, increases. Increases, or rather, let's first observe that what actually then happened here was that the volume was decreased and therefore the pressure increased. So increase in pressure. There was an increase in pressure when the plunger was pushed up because the volume was pushed up. When the volume decreased, the pressure increased. Why? Because volume and pressure are inversely proportional to each other. So yeah, right. So increase in pressure favors the reaction. Increase in pressure favors the reaction. That leads to smaller. Yes. Now take a look at this, because this is the trick the examiners use all the time. You look at the mole ratios. Increase in pressure favors the reaction that leads to smaller number of moles. Smaller number of moles or volume of gas. What is the meaning of this? Or volume of gas. What is the meaning of this? So if you increase the pressure, so increasing pressure favors the reaction that leads to smaller number of moles by Le Chatelier's principle. Moreover, what does this mean? Well, it means that the forward reaction is favored. Forward reaction is favored. Forward reaction is favored. That point? The point is that the number of moles, right? So yeah, because there are 3 marks. There are 3 marks here. The number of moles, right? So the number of moles of N2O4, the number of moles of N2O4 increases. Okay, let's take a look. Okay, now the couple of things, therefore, that are very important here. The couple of things here that remain very, very important. So we are then saying, use the Chatterley's principle to explain the color change observed in the syringe. Why did the color change? What was the color? The color was dark, and then the color became lighter. Okay, what would a dark color mean? A dark color would mean that we have mostly the NO2 that is more visible. And a lighter color would mean there's a shift towards the colorless. Notice the word shift, because that is what Le Chatelier's principle is about. Right, so now I would like us to just discuss these three syringes. First, remember that a certain amount of nitrogen dioxide is sealed in the gas syringe at 25 degrees Celsius, and you have that initially. And then when suddenly this is pressed up, you really can see that you have a darker color, and this darker color means there's a shift towards the side of the equilibrium that is having a dark brown color, which means that we have a dominance of the NO2. And then now, after a while, then it becomes more colorless, meaning that there's a shift in the equilibrium towards the side that has the colorless color. Okay, but also in the way you're explaining it here, we are really saying if we increase increase in pressure favors the reaction that leads to smaller number of moles. Yeah, so if we increase the pressure, right, favors the reaction that leads to smaller number of moles, meaning therefore that the forward reaction is favored, the number of moles of N2O4 increases. This is the reason. Right, so if you increase the pressure, how do you increase the pressure? You increase the pressure by decreasing the volume. So if you decrease the volume, the pressure increases. And when the pressure increases, right, so now it means therefore the increase in pressure favors the reaction that leads to smaller number of moles or volume. Hey, what is this? I want us to discuss this very importantly because we shall be doing a lot of the questions. But now there is this relationship between pressure and volume. So when the pressure increases, the volume decreases. Okay. Increase in pressure favors the reaction that leads to smaller number of moles. So increase in pressure or volume. So now if you increase the pressure, that happens with the decrease in volume. And now, in other words, you have smaller number of moles or what you call smaller volume. Yeah, so when the pressure becomes greater, the number of moles tend to reduce, and therefore the volume also becomes smaller. When the volume becomes smaller, this shift to the side that has the smaller number of moles. The ratio is 2:1, right? So it shifts to the side that has smaller number of moles, to the side of the 1. The forward reaction is favored. Because why? Because it has smaller number of moles. Increase in pressure favors smaller number of moles. Increase in pressure goes with a decrease in volume and goes with smaller number of moles. Small number of moles means the forward direction is favored, and that means the number of moles of N2O4 increases. Number of moles of N2O4 increases, and this is the answer for the 3 box. Okay, we're good. Let's move on to the next point. That was the... Okay, but another student can come and say, hang on, but I have a different answer. I don't want to speak about N2O4. I want to speak about NO2. So the student is going to say number of moles. Alternatively, we can say the number of moles of what? Number of moles of NO2. Okay, because another student can say, why are we only speaking about N2O4? Because this is a reaction equilibrium, so we can speak about any of this, and that is the truth. We can speak about the left or the right. So the number of moles of NO2 right, decreases. Right, so the number of moles of NO2 decreases. So in other words, when we say the forward reaction is favored, meaning the number of moles of N2O4 increases, then another student can say, okay, but simultaneously the number of moles of the NO2 nitrogen dioxide, what is the number of moles doing there? The number of moles there is such that it decreases. Okay, that student will just be on point. Will just be on point. As we proceed to the next part of the question, let us move to the next part of the question and find ourselves some joy in solving more chemistry questions like the next one. Next question. Right, so, right. So now we continue to the next point. Right, continue to the next point. Now, let us look at the fourth part of the question. Fourth part of the question. So the fourth part of the question is going to be discussed. But now, the couple of things that still remain very important as to look at the syringes here. This one is has a specific chemical name. We call the nitrogen. We call it the nitrogen dioxide. We call it the nitrogen dioxide. This one is called, the nitrogen. It's called the nitrogen tetroxide. Tetroxide. It's called the nitrogen tetroxide. Don't want to call it that way. We call it the dinitrogen. Dinitrogen tetroxide. Okay, so in other words, you have certain scientific names that are used. Okay, so the most popular name for the N2O4 is nitrogen tetroxide, but you can always call it the dinitrogen tetroxide to mean the N2O4. Okay, let us answer the questions that follow. Right, but what is the IUPAC name? There's something we call the IUPAC ID. Right, the IUPAC ID is dinitrogen tetroxide. Dinitrogen tetroxide is, or you can call it the strictly speaking, dinitrogen tetra for 4, tetraoxides, dinitrogen tetroxide. That would actually be what we call the IUPAC ID. Right, dinitrogen tetraoxide, well, because the tetra obviously means 4. Let's look at the next point. Let's answer the next question on this particular point. 6.4.1 is the same, is the continuation of the question on the syringes, but now it's just the last part of the question. Okay, the third part is the same. We read that before. The temperature of the reaction mixture in the gas syringe is now increased. Somebody does what? It's increasing the temperature. They're moving it upward. And a new equilibrium is established. How will each of the following be affected? Right, so let us look at this cautiously. But I want us to first discuss in relation to this. Okay, you have that this is the reaction, which is the N2, rather NO2, N2O4, we can see first and foremost, I mean, if we increase the temperature, I need to look at whether it's exothermic or endothermic. Okay, that becomes like the first thing we do. We look at the fact that it is either endo or exo. Okay, that's fine. Right, so if it is endo or exo, we are actually seeing that because of the heat of reaction. Right, so okay, yeah, that is already there. So now it's here, meaning the heat of reaction is less than 0. Now, color of the reaction mixture, right? The color of the reaction mixture, right? Only darker, lighter, or remains the same. If we increase the temperature, because we agree that the forward reaction is exothermic. The forward reaction is exothermic. So now if we increase the temperature, so this was so in which direction will the equilibrium shift? What decreases and what increases? Okay, because it is exothermic, Newell was able to make that observation sometime back to say that since it is exothermic, the equilibrium tends to do what? Right, tends to shift towards the endothermic part. Right, so in other words, we really expect that both the rates of the forward and reverse will increase, but the amount of N2O4 will sort of decrease with the amount of NO2, which will then increase, and therefore it's going to be darker. It's going to be darker. Right, so in 6.4.1, it's going to be darker when we increase the temperature. It favors the endothermic reaction. Right, so if the equilibrium favors the endothermic reaction, then we actually would have a much darker color. The NO2 would actually be most dominant. 6.4.2, value of the equilibrium constant. The case.
So what would
Yes,
I
please.
say? What would I say if they ask to give a reason
Okay,
for
that's a good
your
question.
for
Yes. What would you say if they ask that we give a reason? So once again, an increase, the reason would be an increase in temperature favors the endothermic reaction. Since the heat of reaction is negative, the forward reaction is what? The forward reaction is exothermic, and therefore an increase in temperature will favor the endothermic reaction. Why? It is going to favor, according to the Chatelier's principle, it's going to favor the reaction that will tend to counter the effect. What is the effect? The effect, according to Le Chatelier's principle, the effect is the increase in temperature. So according to Le Chatelier's principle, the reaction that will be favored is the one that will decrease the temperature. The one that will decrease temperature. So which one will therefore decrease the temperature? Is the reverse reaction. Because it's endothermic and now it absorbs the heat, right? And therefore, the reverse reaction is favored, and therefore you'd have that more. So in other words, the number of moles of NO2 would therefore increase, and therefore we have a dark brown color. Okay, there's just too many things we can say there. Okay, but it's all Le Chatelier's principle. Now, if you look at 6.4.2, value of the equilibrium constant Kc. How will the Kc change now in this case? If you increase the temperature, with the Kc, would it increase, decrease, or remain the same? Let's check. Okay, first things first, the Kc is N2O4. You divide by NO2, and you square this. So, Kc is this. N2O4, you divide by NO2 squared. And then now, what is the meaning of this? Now, if you increase the temperature, we expect that the N2O4 will have, its amount will decrease. The number of moles of this one will decrease. And therefore the concentration of N2O4 will decrease. As much as this one is going to increase, but as a consequence, because the numerator is getting smaller, obviously by direct proportionality of the numerator and the numerator, we're going to see most certainly a noticeable, a very observable decrease. So in other words, we're going to say that it decreases. We're going to say that it most certainly decreases there. Okay, so why does it decrease? It decreases because we can see the numerator decreases, and therefore, as a consequence, we are able to make the observation that we have a noticeable a noticeable decrease in the Kc. So the Kc will then decrease. As we migrate to the next paper that we're going to discuss, right, all these papers will be done at the end of the day. Okay, so, right, so now we move to the next paper, and the next paper is a key paper because in our practice, it's very important that we do what? We focus a lot on the national exams. Okay, we can also do the provincial, but the national exams set the benchmark for our reasoning. So we need to make sure that we do lots and lots of the national exams, because the examiners, anyone who sets the exam must follow the national guidelines. So yeah, they cannot deviate from it. There's another question. Okay, we're starting from the end of it, of this document. Then we have this one here. Right, so, okay, we started here. Then we have the other question on the graph. We have this question on the graph. And this question on the graph appeared in one of our papers in the Republic. Okay, this one here is 7.1. And this one here in 7.1, the reaction between hydrogen chloride and oxygen reaches equilibrium in a sealed container according to the following balanced equation. This is it. This is it. Right, so we have the reaction between hydrogen chloride and oxygen, right, that reaches equilibrium in a closed container according to the following balanced equation. As said already, we shall do all the questions. Okay, all the questions are going to be done. Is this reaction exothermic or endothermic? Give a reason for your answer. Right, I know that this one is way too easy. And the immediate observation is that it is exo. We're looking at 7.1. It is exothermic. Why? It is exothermic. Why? That means that the heat of reaction is negative. The heat of reaction is what? Is negative. So if the heat of reaction is negative, or you don't want to say the heat of reaction is negative, delta H is negative here, which is minus 113 kilojoules, or you can say it is less than 0. Less than 0. You can see that the heat of reaction, delta H, is less than 0. Right, okay, we're good. Let's look at the next point. Let's look at the next point. The graphs below. Okay, that's interesting. Okay, the examiner is speaking about the graphs. But now this looks like one graph, but there are two graphs there. Okay, there are multiple graphs. There's a graph here that starts from the 1.0, and there's another one that starts from 0.3, and it goes down. Right, not drawn to scale, show how the amounts of reactants present in the container change with time at a specific temperature. So the graphs below, not drawn to scale, show how the amounts of reactants present in the container. So we're dealing with the reactants. So we're able to see that, like the hydrogen chloride gas, it's this one here initially, but you can see the how the amounts of the reactants present change with time. So this is the HCl, the amount of the reactants. 1.0, there's a decrease there. We start from 1.0 as the number of moles of HCl, and then so these are like real number of moles. These Right, so the volume of the container is 5 decimeter cubed. We're good. Let's continue. Right, how does the rate of the forward reaction at time t1 compare to that at time t2? Write down greater than, smaller than, or equal to. Use the graphs to give the reason for your answer. How does the rate of the forward reaction at time t1 compare? So now there is time t1 and then there's time t2. Obviously, it's time t3 there. But how does the rate of the forward reaction at time t1 compare to that at time t2? Write down greater than, smaller than, or equal to. Use the graphs to give a reason for your answer. If you look at the 7.2.1, right, there are a couple of things you need to take into account. We are speaking about the rate of the forward reaction at time t1 compare to that at time t2. Let's see. Right, so this is time t1 and there's time t2 there. Right, so if you look at that very, very carefully, we're interested in the rate of the forward reaction. What is the rate of the forward reaction? So the rate of the forward reaction in this case would mean we're starting with the reactants HCl and oxygen. But now you really can see, therefore, that each one of them, this graph shows us the amount in moles, the moles decrease. The moles of HCl decrease and the moles of O2 decrease. And if the moles decrease, equilibrium is reached at some point, right? So if equilibrium is reached at some point, now we are asking the question, how does the rate of the forward reaction at time t1 compare to that at time t2? The rate of the reaction here and the rate of the reaction there. At time t1, there's a rate of reaction at time t2. Right, let me just remove this little bit. I want us to analyze this quite carefully. Quite carefully. Right, so because we are able to see that there's a decrease from the beginning, and there's a further decrease after time t1. So now the rate of the forward reaction at time t1 compared to that at time t2. Okay, because you're able to see that here the rate at which these because the rate is the number of moles, or change in number of moles divided by change in time. Here you really can see that it's quickly going down, but here it's about to be level. It's about to be level. So in other words, here the rate, it was faster, right? It was a greater rate, so you need to use the word greater than, smaller than. So it was a greater rate because here now you can see that it's becoming more level. So because of that, then in 7.2.1, it was greater than. It was greater than. Okay, it was greater than. As a matter of fact, we used to use the word greater than, so it was most certainly greater than. Right, because the slope is larger. Use the graphs to give a reason for your answer. Right, so now let us give a reason for this answer. Right, so and the reason for the answer is that we have the steeper gradients. Right, so we have what you call steeper gradients, slopes. Steeper gradients, slopes. Steeper gradients, slopes. Right, so Right, so that is the thing. So because of the steeper gradients, slopes, and that would sort of be the reason. So as a matter of fact, then you'd have 1 mark for the greater than and 1 mark for the steeper gradients or slopes. Yeah, take a look at that and make sure you sort of are able to understand that part. Let's move to the next question. So the next question is 7.2.2. How does the rate of the forward and reverse reactions compare at time 3? Right only greater than, smaller than, or equal to? We analyze that. So now in this question, we're saying, how does the rate of the forward reaction, right? So how does the rate of the forward reaction and reverse reactions compare at time T3? Okay. Right, so we can see that the graph is now level. The graphs are both level. HCl, it has leveled up, and the O2, it has leveled up. So these guys here are equal to each other. So you can say equal to. Right, they're equal to each other. How do we know? Because you can see the level here. So obviously the rate was much faster here, but now you can see the rate is constant. Constant, right? So the rate of the forward and reverse reactions occur at the same rate. Constant. Okay, we're good. Next question. Okay, we're good. Now, okay, we're looking at a 7.2.3 right now because we've already looked at the other parts of the question. Right, 7.2.3 is the next story. Calculate the equilibrium constant Kc for this reaction at this temperature. Okay, we excited. Kc calculation. We have a chance to practice. So now, to calculate the Kc here, there are a couple of things we need to take, into account. What is it? HCl. So 4HCl plus O2 gas two H2O, 2Cl2 gas, okay, so we have the reaction. We want to calculate the thing, the equilibrium constant. Right, dealing with the reaction, what else are we dealing with? We are dealing with the initial thing, initial moles, or what you call the initial quantity. Right, so dealing with the initial quantity. Right, so the initial quantity, in mole. Now, the initial quantity in mole, what then is this here? Right? So we know very well that we're going to be dealing with the initial things, like we read the actual very nice question, this one. Very lovely question, but it offers us like perfect practice. There are those questions that when you go to the other provincial ones, then they're going to be a bit even much more easier. Because we're starting with HCl, and HCl is this one here. HCl starts at 1 mole. So we have 1. And then oxygen. Oxygen is at 0.3. We're good. We're good. Okay. So we're so good. And then we have naught and naught. Okay, we're good. Just drawing some tables, separating these things here. Right. Let's see. Horizontal, then the changes using the rise technique. Then we have the change. These changes in what? Is in mole. Okay. Right. What have they given us, if anything? We know an equilibrium value, 0,1, but we know this one for oxygen. Right, so we know the actual equilibrium amount for oxygen, right? So we're going to do that. So they're giving us something a little bit. Quantity at equilibrium. Quantity at equilibrium. Quantity at equilibrium in mole. Okay. Quantity at equilibrium in what? In mole. Okay, we're good. Okay, let's deal with that one. Okay, we have been given, these are the moles right now. Yeah, the 0,1 is for what? Is for oxygen. So oxygen at quantity at equilibrium is going to be exactly 0,1. Oxygen, 0,1. And then we have the, okay, we're going to get the other one because now here for HCl, hydrogen chloride gas is not given, but yeah, for oxygen. But now, because we know the quantity at equilibrium, then we can be able to get the change. So now, how much was the change? So the change was negative, because we're starting with these things here and you get there. So it's negative 0,2, because 0,3 minus 0,2 is 0,1. Okay, so you can put the signs here. We're starting with the HCl and the O2. Then we also have something. Okay, remember the mole ratios. What are the mole ratios here? Okay, we good with the mole ratios. Right, what are the mole ratios? So the mole ratios, it's 4:1:2:2. 4:1:2:2. We good. Hey. Okay. Okay. Right. Now, what would the change be? So we reason this change up, because now if we agree therefore that this one, so but with this one, it's gonna be double this. So if it is 0.2 here, this one is gonna be double the 0.2, which is gonna be 2 times 0.2, and 2 times 0.2 is 0.4. That is plus. And this is plus 0.4 as well, which is double the 0.2. But what about this one here? This one is negative, but it's 4 times. So it's going to be negative 4 times 0.2, which is minus 0,8. Change is 0,8, negative. We good. Okay, let's check. Now, okay, the only clue that was given was one thing at equilibrium and the initial things. We know the beginning of the initial quantities, and then one quantity
But,
for,
so
yes,
can you please explain these values?
like
Negative 0.2 is, how did you get them?
okay. How did I get the values? Okay, good. Right. So these values themselves are such that they're obtained with ease. How else can be obtained? Okay, I'm going to use another technique we use. That's fine, but I'm going to use another technique we use, because these values, we did not know them before. We did not know them before. We knew the examiner gave us quantity at equilibrium 0,1, quantity initially at 0,3. So now what do? We use the mole ratios. So we can come here and say, because this one is what? It's the mole ratio. 4:1:2:2. Yeah, we can say minus 4x. This one, because it's only 1. 4:1 minus x. 2x to x, like this. Okay. Right, so next. All right, so yeah, this is what we do. So now at the end, now we have all these things. This one is plus 2x, and this one is minus. Then now we need to get these values, but the only way out is this one, because here we know everything. So we can take the 0,3 and we minus x, because it's 4:1 to 2 ratio. So if we add these things, we combine this and that. 0,3 minus x is equal to 0,1. And then now x is 0,3 minus 0,1, which is 0,2. So in other words, that means that this one is going to be what? It's going to be like minus 0,2. Let me do it in green color. Right, otherwise everything is going to be just red. So here you're going to have minus 0,2. Okay, the x is 0,2, but why is it negative? It's negative because it's on the reactant side. That is what we're starting with. So it's going to be reduction on the reactant side, and then there's going to be an increase on the product side. So obviously at this point now, we're going to do x is 0,2, but multiplied by 4. So we have 0,2 times 4, which is minus 0,8. 2 times 0,2, 0,4. 2 times 0,2, 0,4. But these things now, they're plus. This 0,4, they're plus on the product side, because the product will increase when the reactants now they will decrease to reach equilibrium, because these products had nothing in the beginning. So now, because of the changes will contribute something towards the product, so that in the end, then we have these products being formed, and then the reactants become formed, and now we have equilibrium, forward, reverse, and so on and so forth. Okay, we're good. I want us to talk about something interesting. Right, so we good. Let's look at the quantities at equilibrium. Okay, now it's easy because we already know the initial and the change. So now this is like 1 minus 0,8. Okay, this one you know is 0,2. 0,3 minus 0,2 is 0,1. 0 plus 0,4. 0,4. 0 plus 0,2 is 0,4. Okay, we're good. Now, there is equilibrium concentration. Equilibrium concentration. Okay, so now we have the equilibrium concentration. Okay, now with the equilibrium concentration, what do we get? We use our old formula. Concentration is number of moles and volume. That's what we use. Okay, we already know the volume is sitting at 5 cubic units. So which means that cubic decimeters. So which means we take the number of moles and we divide by 5 and we get the answer 0,04, which is 0,1 divided by 5, 0,02. 0,4 divided by 5. Okay, yeah, because you take the number of moles, divide by 5. Everything divided by 5. The volume is 5. Everything is divided by 5. So, and this one is going to be 0,08. We take the 0,4 divided by 5. 0,08. Good. Yes. This is the answer. It is the answer. It is the answer. Now, we got everything here. So we need calculate the equilibrium constant Kc for this reaction at this temperature. Okay, at equilibrium, we have all the concentrations. Woo, we excited. We are more than happy because now We want to calculate the Kc, but we have everything at equilibrium, all the concentrations at equilibrium. And then we could proceed to then say the concentration, according to these, everything is it's gas, 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 gas. So we're good. So which means that we're going to now start and say with water, like water vapor, because it's water, but it's a gas, right? It's water vapor that is running out of the conversion of water to a gas from the other states, liquid and potentially solid as well. Okay, so we square it, and then here, okay, is this balanced? Okay, the examiner said the following: balanced. Okay, the examiner had to tell us this because we can try to balance this, and students can try to balance this and really mess things up. Okay, and waste time there, but the examiner told us it's balanced. So we have Cl2 balanced, squared. HCl to the 4th power. Kc. H2O4 or H2O, excuse, 0.08. 0.08. You square this. And then the Cl2, 0.08. You square this. And then the HCl, okay, it's here. 0.04 to the 4th power. Oxygen, 0.02. Okay, this one is it's a good question. So it's shedding a lot more light on one of the provincial questions we did together from the Gauteng province that you brought. So if a student can do this one, because it has the actual number of moles, like initial number of moles, that can be read from the graph, but not given in the story. You know, the examiners sometimes do this. And that was the situation of that question that you came from Gauteng, that you gave last time. So you had the number of moles that was given in the question, so it's 0.08, and you square this, and then it is 0.08. You square this, and then you have 0.04, and then you raise it to the 4th power. Okay, good. You close like this. You raise it to the 4th power. And then we have 0.02, and you get this. Okay, so this Kc value is big. It's so big. It's 800. So now it means that our Kc is actually 800. Okay, but remember it's dimensionless, so it is just a number. There are no units. Right, it is without units. So we have to calculate the equilibrium constant Kc for this reaction at this temperature. Remember, this is one of the questions from your paper. Once again, this one is a very good question. If a student can do this question, meaning sometimes the examiners can give you a story and not give you numbers. There are no numbers of moles in the story, but yet the numbers of moles are actually given as part of the graph and can be read off from the graph, like the initial number of moles, which we're able to take from the graph. Note that we take the initial number of moles from the graph, we put them as part of the table, and then the examiners give us a hint, because if they give us the initial only, we can't proceed. We can't proceed. So they must give us something more, either at equilibrium, and they gave us something at equilibrium. Yes, they gave us for oxygen. They said oxygen is not comma 1. So we're good. Excited. 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 Okay. Next question. Next question. Right. Right, the next question is a very interesting one, and it is right now the question 7.3. Because the previous one was the Kc in 7.2.3, which we've already done, and we got that Kc was actually equal to 800 for this one. And then here we proceed to the next one, where, what question number is this? Need to make sure, I'm trying to make sure we don't jump questions. So this one is 7.2.3, and then this one is 7.3. Okay, from 7.2.3, then the next one is 7.3. Okay, this is consistent with the actual document. I'm just looking at the question paper here. All right, so if you look at this 7.3, the temperature is now increased. The examiners are very, very famous when it comes to this. They decide to increase the temperature, but this one is exothermic. Okay, we have not yet answered any question, but it is exothermic, and now we are increasing the temperature. Temperature is up. How will this change affect the value of the equilibrium constant? Write down increases, decreases, or remains the same. Explain the answer. Okay, let's take a look at this one. Let's take a look at this one. So we're looking at the question 7.3. Right. Yes. How will this, so the temperature increases, how will this change affect the value of the equilibrium constant? First things first, equilibrium constant is concentration of the products and concentration of the reactants. O2. O2. Okay, so right, so now, okay, we're good. Let's continue. Okay, this is what we have. So if we increase the temperature, what is happening to the amount? Okay, now I want you to note something that we said together last time, and this was one question you brought here about SO2 and oxygen, and then SO3, something like of this sort. Right, something about the contact process. Right, so something about the contact process that you brought last time. Now, if you recall, I want us to discuss this question in relation to that, and then we shall move on, and then say, okay, we're just good right now. We just actually, obviously, we'll be discussing this question in detail, but right. Remember last time we looked at the contact process, right? The contact process, and we went on to then say, in view of the contact process, there are a couple of things that remain very, very important for us to take into account, but also the contact process is used in the production of, is part of the steps that is used in the production of the what? Of sulfuric acid. Okay, that's fine. We shall spend some time on that. But I want us to now just discuss this quickly. And then say, 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 what is going to happen to the amounts? Okay, the rates of the forward and reverse reactions will both increase. This is very important because they're going to be going to some other questions where they ask you about the rates. So if you have an exothermic reaction and then you increase the temperature, both rates will increase, but now the amounts of these will decrease. So in other words, the amount of water will decrease, but also the amount of the chloride gas will also decrease. So now if they then say, write down what is going to happen to the value of the equilibrium constant. So we can see that the products will decrease in the amounts, and the reactants will therefore tend to increase. And as a consequence, because the numerators decrease themselves, we are excited to say there's going to be a decrease. There's going to be a decrease. Why? There is a decrease because the forwards, because the amounts of the or the number of moles of the products will decrease. But because if this is exothermic, an increase in temperature favors, according to the Lechatelier's principle, if the temperature increases, the reaction will tend to shift to the side of the equilibrium that will counter the increase that is going to consume the temperature that is being contributed. So you're contributing temperature increase. So now in the end, there's going to be a decrease. there's going to be a decrease. Decrease in what? There's going to be a decrease in the case C, because the concentrations or the amounts of the products will decrease. Next question. Right, the next question is 7.4.2, 7.4.1. How will each of the following changes affect the equilibrium concentration of Cl2? Write down increases, decreases, or remains the same. Water vapor is added into the container. Okay. They decide to add this one. So if they add water vapor, they add this water as a gas, and which is water vapor, right? So if they increase the H2O amount, how will each of the following changes affect the equilibrium concentration of Cl2? How will this affect the Cl2 concentration? Right, so we're able to see, therefore, that if you add more water vapor, what is going to happen to the Cl2? The truth is, in 7.4.1, there's going to be most certainly a noticeable decrease. Why? There's going to be a noticeable decrease. Right, so let me see here in 7.3. Okay, I wanted to say more here because the marks are 4. All right, we noted obviously that there's going to be a decrease, but let us say more. So we're saying a decrease is number 1. Number 2, we're saying higher temperature, let's say that. So we could say higher temperature favors the endothermic. Higher temperature favors the endothermic reaction. Okay, we stated that, but I'm trying to write that one down because the answer would be decreases and then the explanations. Higher temperature favors the endothermic reaction. And we mentioned these, but write it down. So the reverse reaction is favored. The reverse reaction is favored. The reverse reaction is favored. Less products. Less products. They're going to be less products or more reactants. Yeah, that's what we said. More reactants. So the reactants will be more because now this favors the reverse reaction. So there are more reactants and there are less products. That's a point. The reverse reaction is favored. That's a point. Okay, remember there are 4 points. And then a higher temperature favors endothermic reaction, which is the reverse reaction. And obviously the Kc itself decreases. Yeah, those will be all the points for the 4 marks there. Okay, I stated them verbally, but I feel that it's very important that we write them down. We write them down so that you're able to sort of, okay. Now in 7.4.1, we are saying how will each of the following changes affect the equilibrium concentration of CO2? Okay, if you just increase the amounts or the amount of one of these, so you put more water vapor in there, in the reaction vessel. If you put, now, how will each of the following affect the equilibrium concentration? Water vapor is added into the container. You add water vapor into the container. Adding water vapor into the container means, therefore, according to Le Chatelier's principle, the reaction that will counter, that will oppose the change will be favored. So the reaction that is going to decrease is going to be favored. So in other words, it means that the reverse reaction will tend to be favored. So if the reverse reaction is favored, what is it going to do? So it's going to drain both of these guys. It's going to drain the products. It's going to reduce the products, and therefore there's going to be such that the there's decreases there. So 7.4.1, therefore the water vapor is added into the container. If the water vapor is added into the container, they certainly a decrease. They certainly a decrease in the Cl2 gas. So this one is going to also decrease. Right. So obviously, I mean, it's going to decrease because the acrobatics here. So the Cl2 gas, it's going to decrease at the time that the water is spiking up. The water vapor is spiking up. We are adding more water vapor into the reaction mixture. When that happens, there's more water vapor. But the other one is going to decrease. Why? It's the Chatelier's principle. If we increase one of these, the reaction that is going to counter the change is going to be favored, meaning it's going to be the reverse. The reverse is going to be eating. It's going to be eating on these. For it to increase, then it's going to be biting these guys. So if it's taking a bite from here, a bite from there, building the left, taking a bite from here, building the left. So as a consequence, we expect these two guys to decrease. When this one decreases, because now an equilibrium it will try and sort of be established. This reaction will try to establish an equilibrium. In the process, then it's decreasing both of these guys. Okay, next point. What about if somebody decides to add a catalyst? Somebody takes a catalyst and puts it in there. What happens if a catalyst is added? Right, a catalyst, what does it do? It increases the rate of the reactions. So in other words, the rate of the reaction is going to increase. So if it increases the rate of the reaction, what does it do to the following? How will it affect the equilibrium concentration of this? We note that at equilibrium, what happens at equilibrium? At equilibrium, concentration is number of moles on volume. We note that according to these two graphs, the number of moles here will remain constant, and also the volume remains constant. If this one is constant and that is constant, it means the concentration is constant, and therefore at this point we are confident to say it remains the same. We're good. Remains the same. Remains the same. Remains the same. Remains the same.
So can you please repeat again?
Okay, good. Right. So at this point, we are effectively saying that what is happening here? A catalyst is added. Okay, if in this reaction mixture a catalyst is added, what does the catalyst do? What does a catalyst do? So a catalyst speeds up the rate of the reaction without taking part in the reaction. So at this point, it's gonna increase the rate of the reaction. But now, when the rate is increased, remember, concentration is number of moles on volume. If we know that concentration is number of moles on volume, what do you say from the graph here? The number of moles of HCl will remain constant. The number of moles of oxygen will remain constant. And also, as a consequence, then, there's more with the graphs you can say here, because the examiner did not show us here. The truth is, like with most of the graphs, this graph is not even complete, you know. This graph is only showing us what? This graph is only showing us the reactants, but the graphs in general can even show the products. So at some point, even the number of moles of the product that's going to be formed will be constant as well. So when the number of moles of the HCl is constant, the O2 is constant, the water is constant, the chloride gas is also constant, it means that the number of moles is constant. Okay, but also if the number of moles is constant, the volume is also constant. Why? The volume is also constant because we're not told that the size, the volume of the container is changed. Okay, I'm trying to say the number of moles and the volume are both constant, which means that concentration itself is also constant. So if concentration is constant, now we are asking the question, the equilibrium concentration of Cl2, how is it going to change? So adding a catalyst is not going to change because now you are really able to see that the number of moles is constant, the volume is constant, and therefore the concentration does not at all change. So the concentration therefore remains the same. because concentration is number of moles on volume. Both number of moles and volume are constant. So it means that the concentration of Cl2 remains constant when the catalyst is added to a reaction mixture. You can ask a question. Let's look at 7.4.3. Right, so in the next question now, we're asking 7.4.3. The volume of the container is increased. Let's see. Concentration is number of moles on volume. Now we're saying the volume of the container is increased. Somebody pushes up and increases the volume of the container, and we know very well that in case the volume increases, we expect a decrease in the concentration. So at this point, it means what? It means the equilibrium concentration of Cl2 does what? It decreases. It means, therefore, that the equilibrium concentration of Cl2 does what? Decreases there. So you take a careful look at that and make sure that obviously you are able to interpret that and you are able to make sense of that. Right, so any question on this so far? Right, so take a moment to think about what is happening here and try to make, okay, this question is a very, very good question. It is an awesome question that is a question that must be most certainly understood. And I want us to look at the next question. There are too many questions here. All right, I want us to look at the next question. I believe you
So
said,
why is it decreases?
okay, that's a good question.
They're
Why
saying
does it,
the volume of the container is increased. So when you're saying the
the
concentration
volume,
decreases,
yes. So because
and
concentration, yeah,
so
the
when the
volume
volume
is increases,
increase,
the concentration does what? Decreases. Okay,
is it the concentration for everything,
okay, that's a good
or
question.
you're looking at Cl2 only?
Only. Okay, that's a good question. Is it the concentration for everything, or it is the concentration for everything? Very powerful, very powerful. Why? Because everything is in one container, you know? And then if everything is in one container, if somebody say the volume is what? The volume is increased, right? The volume is increased. How would one increase the volume? Maybe they double the volume, you know? So if they increase the volume, then there's more room. Maybe, you know, if this was a plunger like this, a plunger like we saw the syringe, and then now somebody's going to have this, and now they increase this by pulling up the plunger. You see, when they pull up the plunger, what then happens? When they pull up the plunger, then the volume is large. When the volume is large, it means there's more room for everything. Okay, so there's more room for everything, and then now it means these gas molecules are more free, they have more space. If they have more space, what does concentration mean? Concentration means they can be concentrated in a corner, and concentration has to do with the amount of solute per decimeter, per cubic decimeter. So in other words, now if you then say, okay, you increase the volume. If you increase the volume, then it means that you are making them more free to move because they were pressed to each other. It's like if you can have people here, if there can be people in this thing, and then now the room is small. If the room is small, the people will be closer to each other, and this means the concentration is, the people are more concentrated in this small space, But now if the room is big, then the concentration is going to be less. So when you make the room big, it means that you are such that, because you are making the room big, how do you make the room big? You are most certainly increasing the volume. The concentration is going to be small. The concentration small means that the people are not going to be packed. The people will have more room, they'll be free. But when the people are free to move around, it means that the concentration is less. They are not packed. Concentration is being packed. So if they're packed closer to each other, but it's the concentration of everything here, because everything is inside the container, you know? Okay, so my point is, if we then decide to say we increase the volume, then the concentration is going to decrease, because it means that these gas molecules are not going to be pressed against each other. Concentration means they're pressed against each other. Now the concentration is going to be less. They're more not packed, they're not congested. They're free to move. But if all the molecules of these gases, because all this is just a mixture of gases in a container. Right. So, because remember that this oxygen reaches equilibrium in a closed container. In a closed container. Sorry. I want us to look at another question. You still have energy for us to continue, or yeah, you still have energy for us to do another question, okay? Because we just finished this
Yes,
question.
we can
Yeah.
continue.
Okay, fine, thanks. I want us to do another question from one of the from your questions here. Okay, you sent that question and then we're going to discuss it. We discussed it last time, but I think it was a little bit tricky. So we have a chance to discuss it right now. And it is, okay, there are many questions. Some of the questions, I'm going to send you the videos of those questions, you know. And some of the questions which we might not have a chance to do today, we're going to do during the week. I'm going to make time during the week. And then we can do some broadcasts, you know, and make sure that we sort of are able to understand those questions. Okay, there's a question I'm going to load now. Just a minute. There's some question I'm going to load now, and this question that I'm going to load right now is a question right, that you gave to me last time, but yeah, I want us to do it. I want us to do it. Right. So, right. Okay, let's see. Okay, just one question, please, or one moment. Right. So we're gonna discuss this one. I'm loading the question in then, and then. Right. So it is exactly this. Let's see. Right, so yeah, this one we've already done, and let me see. Okay, there's this one, and then there's this other one. Okay, let's see. Yeah. Okay, now. Okay, yeah, is this one. Okay, let us do this one, because you sent me this question, and this is the contact process that you brought, and then now we had we discussed it, but we just have a chance to calculate a little bit. Okay, it's not very long. It's question 7.4 from the November 2010 paper, the year of the World Cup in South Africa, where everybody was excited. Everybody was like, woo, woo, the World Cup is coming to South Africa. And Neo, by that time, was still in primary, you know, because it was nearly 14 years ago. Okay, you're still like in primary, but yeah, okay. So this is the question. And it's 7.4 that we're doing. Right, the reaction we have here below represents the catalyzed step in the contact process. Right, so in the contact process, we have that, sulfur dioxide reacts with oxygen to form SO3, and the heat of reaction is negative. The reaction takes place in a closed container and reaches equilibrium at 427 degrees Celsius. How will a higher temperature affect each of the following? Write down only increases, decreases, or remains the same. 7.4.1. The rate of production of SO3. The rate of production of SO3. Okay, yeah, remember we looked at this question together. Okay, what is happening here? The reaction takes place in a closed container and reaches equilibrium at 427 degrees Celsius or centigrade. How will a higher temperature? Now, the temperature is increased, and how will it affect each of the following? You need to write down only increases, decreases, or remains the same. So, if somebody decides to say in this particular reaction, what do they do? They increase the temperature. It was 427 degrees Celsius, but now they make it maybe 500 or something more than that. What then would happen here? Right? You're able to see. Let's analyze together. This is what we said now. Okay, remember this reaction is exothermic. So an increase in temperature, according to the Chatelier's principle, will favor the reverse. Okay, but what is it going to do to the rate of the forward and the reverse reactions? The rate of the reverse is going to increase, increasing the rate of the forward. The rate of the forward and reverse will increase until a new equilibrium is established. Because the disturbance is an increase in temperature. So we're going to have that, obviously, it's going to be disturbed, this. It's going to be disturbed. The equilibrium is going to be disturbed. So which means that the rate of the forward and reverse will increase. So the rate of the production of SO3 increases. Take a look.
So why does the rate increase? Like,
yes, why does the rate
how?
increase? Okay, you see, that is what I want us to discuss, because you sent this question last time. How does the rate increase? Because we know very well that an increase in temperature will favor the reverse reaction, and therefore it will such that it will increase the rate of the forward and the reverse reaction simultaneously. And so, because first, if the temperature increases, it favors the reverse. And then when the reverse is a lot, then the product will decrease here, building more of these. But when these are built up, then they form the product, and the products break down the reactants. The reactants form the product, and therefore, as a consequence, then the rate of the forward and reverse reactions will therefore in turn increase. Think about it. Okay, now what about the amount, the yield? Because an increase in temperature, according to the Chatelier's principle, favors the reverse, favors the endothermic reaction. An increase in temperature favors the endothermic reaction, which means now the yield of SO3, the yield of the SO3 is such that the SO3, its yield decreases. Why? Well, the rate increases, the rate of production of SO3 increases, but the yield decreases. Okay, so this is what really happens. The yield decreases. Why? Because in the end, when the reverse reaction is favored, because the endothermic reaction is favored, because the forward reaction is exothermic. So the reverse is favored, meaning this one is going to be eaten up. Okay, if you look at the change, what will the change be if we do the calculations here? Okay, if you get the change row in the table, this is going to be minus 2x. This one is going to be x. This one is going to be plus 2x. And this one is going to be plus x in that table. Okay, so yeah, this is what you're going to have. This is what you're going to have. This is what we're going to have. So look at 7.5. This is what we have. Okay. Right, we proceed.
So why do you say plus 2x and plus x? Is it because
Because
it's
because now we are looking at the fact that we are looking at when the temperature does what? When the temperature increases, the kind of
the
disturbance,
reverse
the
reaction is
reverse is
favored?
favored. Yes, the reverse is favored, meaning that we're gonna have the SO3, the yield of the SO3 decreases. If the yield
Okay.
of SO3 decreases because the reverse is favored, it means the other yields will what? Will increase. So it means the oxygen is going to increase, but also the SO2 is going to increase. And this is going to happen at the time that there is a what? There's a higher temperature. At a time that there is a higher temperature. Okay, but obviously, I mean, under normal conditions, you'd expect that these are minus, this is plus. But this only happens when the temperature now is higher, and it does the opposite. That is why in the 7.4.2, then the yield of the SO3 is going to decrease. So SO3 decreases when SO2 and O2 increase, you know?
Okay.
So yeah.
So here it's like we are doing like working in the opposite way.
Well, we are working in the opposite direction. Working the
So it only applies with temperature. If there's like if the equation is exothermic and then they increase temperature.
yes, most definitely. I'm happy that you're able to see that. Why? Because in particular, temperature is the only thing that changes the Kc. Okay, what changes what causes the Kc to either increase or decrease? It's nothing else. So in principle, it's only temperature that is the kind of change that changes the Kc. The rest, if you add a catalyst, you increase the pressure, etc. You know, we know very well that the effects of those, actually, as much as they can disturb an equilibrium, but they do not change the Kc, but it is temperature that has the power to change the Kc. Many times we say it is only temperature. That is the belief in chemistry. It's only temperature. If you want to change the Kc, just change the temperature. That's all. Keep adding catalysts and expecting the Kc to change because it's not going to change. All right. We'll move to the next question. Right. So the reaction is investigated on a small scale in the laboratory. Now let's look at 7.5. So the reaction is investigated on a small scale in the laboratory. Initially, 4 moles of SO2 and an unknown mass, X, of oxygen are sealed in a 2 cubic decimeter flask and allowed to reach equilibrium at a certain temperature. Okay. Right. So we have SO2. We have reaction. And then we have initial. We have initial quantity. We have 2 SO3. Okay, now let's start with this one. So now, if you're looking at this case, what is happening here? Okay, let's just draw this table. That is the reaction, and this is the initial, and then you're going to have the change here. Right, and then you have the change, and then you have what? You have the equilibrium quantity, or what you call, normally we call it the quantity at equilibrium. Right, so in moles. Right, so we have the quantity at equilibrium. Quantity at equilibrium in moles. And then we have the concentration. We have the concentration. The concentration at equilibrium. Right, concentration at equilibrium. Let us finish this up. Okay, so right, so now let us fix it. Let us fix it. So now, Okay, so now you dealing with the reaction is investigated on a small scale in the laboratory. Initially, we have, okay, yeah, let's deal with what we have initially. So initially you have 4 moles of SO2, okay? SO2, we have 4 moles initially. And an unknown mass X, right? So we have an unknown mass X of oxygen are sealed in this particular 2 cubic decimeter. Okay, we're starting with that. And in the end there, you have 0 here. Right. So if this mass is there, we know that number of moles is mass over molar mass. The mass here is the number of moles times the molar mass. Okay, this mass is number of moles times molar mass. Okay. And then if this is exactly the case, okay, we can use number of moles. Okay, because we have just that, it's fine. Right, so now let us have the number of moles is mass over molar mass, and this mass is what? The mass is X. What is the molar mass of oxygen? It's O2 we're dealing with, so it is 2 times 16, which is 32, which is the molar mass of oxygen, over 32. Over 32. Okay, and then this one is 0. In the beginning, there was just no product with only the reactants. Okay, yeah. So we use this formula, number of moles is mass over molar mass. We're given the mass of the oxygen. Right, so now what about the changes? What else have we been given? Okay, let's continue. Initially with that and that. Allowed to reach equilibrium at a certain temperature. At equilibrium, it is found that the concentration of SO3 present in the flask is 1,2. 1,5, excuse me. Right, so at this point, if you then have the concentration of SO3, it's 1,5. So the concentration of SO3 is 1,5. And then you have something else. Okay, so yeah, but this one was there in the beginning. Okay, yeah. And then now you need to deal with the changes, and the changes are a little bit tricky. But you know very well that is 2 is this. 1:1 is to 2. 1:1 is to 2. Okay, let me see. Okay, sorry. 2 here. 2:1 is to 2. Okay, so yeah, let's have that. 2:1 is to 2 because you have 2 moles. 2 moles of SO2, so yeah, 2:1 is to 2 mole ratios are gonna help us deal with these particular changes. So now this is what we have here. Okay, let us analyze these together in terms of the mole ratios. Okay, right. So what do we then have if this is the case? Okay, we have, okay, this is the only lift we have. It's our transport to the answer. The transport to the answer, we work backwards. We work from the equilibrium. And then now we can get the number of moles at equilibrium. So another way to do it. So we then say concentration is number of moles on volume. Let's do that. So concentration is number of moles on volume. We want the number of moles, meaning number of moles of SO3. Number of moles of SO3 is concentration by volume. Right, what is the concentration here? 1,5. Okay, concentration of SO3 is 1,5 times the volume. Right. Right. The volume is what? It's actually 2 cubic decimeters. And therefore, this is 3 moles. So yeah, this quantity is 3. Okay, at equilibrium, 3. But therefore, because if we're looking at the forward, it can only be 3 here, so that when you add these things, you get a 3 here. Right? So now we are in business. Once you get to this point, we worked from the bottom up, we worked from equilibrium. Now we're dealing with the changes. The changes we just actually using the mole ratios. So if this one is 1:2, 1:2, it's a very interesting one. And this one is 3. What will this one be? So you like divide by 2. Divide by 2. So if you divide 3 by 2, you have 3 divided by 2, which is 1,5. So which is 1,5 of what? Which is 1,5 of the number of moles of the oxygen. And then, okay, remember there's a 2 here, please, because it's 2SO2 plus O2, 2SO3. So this one is 2SO2, 2SO3. So this one is also going to be 3 because it's like 2:2, 2:2, like same, okay? Right? Okay, good. We're happy. But now remember, we're looking at the forward. So we're good. So now the forward reaction, therefore, these ones are decreasing. So the changes are like negative. Negative changes and then positive change. So this one is going to be 3. It's 4 minus 3, giving us a 1. And then x on 32, you minus 1,5. X on 32, you minus 1,5, and then this is 3. Now, okay, what is the concentration? Concentration is this guy here. We're going to use this giant formula, our old friend. Concentration becomes number of moles on volume. So concentration is number of moles on volume. It's going to be this over value, which actually is 0,5 here. And this one is concentration, which is number of moles on volume. How complicated it looks like. X minus 32 minus 1,5. You divide by the volume. Okay, concentration is number of moles on volume. Okay. And then now we're good. We have all the concentrations, 0,5 together with these, And now calculate the mass of O2 initially present in the flask if the equilibrium Kc at this temperature is 4,5. We good. So we're going to continue this and say on the next slide, we have Kc for this one. What is Kc? Kc for this one is SO3 squared. That is the product you divide by the reactants. Okay, moving it a little bit to the margin. So, okay, for this one, we know very well. Kc is actually SO3. You square this. You divide by the concentration of the reactants, which is SO2. You square it, and oxygen. Okay, this is exactly what we have. What is the Kc? Is this one, 4,5. So you're going to do here 4,5, and we have SO3. What is SO3? SO3 is like 1,5, you square it. Right, so it's 1,5, you square it. So you're going to have here like 1,5, and then you square this, divided by SO2. What is SO2? SO2 is this one, 0,5. You square it. 0,5, you square it. What is oxygen? Oxygen, it's this one. It's exactly this. But yeah, this you can simplify. You can simplify. Multiply the top and bottom by 32. Multiply by 32, you have x minus. Multiply by 32, you get what? You get a 48. Divided by 64. Multiply by 32, 32. X minus 48 out of 64. Which is exactly x minus 48 divided by what? By 64. Okay, so we have this. Now, okay, we have this, and therefore we can just solve for x. How do you solve for x? We cross multiply to solve for x, which is x minus 48 divided by 64. This is 1,5. You square this, divided by 0,5. You square this, and then we have 4,5. It sits in the denominator, so it's going to come here, and this guy is going to go there. Okay, we're good? Okay, I'm going to launch a calculator quickly, very, very straightforward, and then we just get the value of x. And we're just practicing with this one, but it's going to give us exactly the number of, or rather the mass in the beginning. Okay, we're good. Let's check. We're just going to do this giant division. Taskbar. Launching that. So now let us do calculator practice. So what is it? It is exactly 1.5, you square it, divided by 0.5, you close, you square it, you multiply by 4.5, and then you have the result. Okay, nice. Just two. Nothing more, nothing less. Just 2. So in other words, we have x minus 48 to divide by 64, which equals 2, which means that x minus 48 multiply, which is 128. X becomes 128 plus 48, which is actually what? Oh, okay, we're good. So now, okay, let's see what we're getting. So if you say 120 plus 48, we can use it. Yeah, we can just be able to do that, I know. So in other words, we have the following. So we have exactly the following. Right, so we have exactly the following. Just in a second. Right, what do we have? Right, so we have the following, and what is it? We have exactly 128. We add 48. And therefore, it is 176. 176. Okay, remember, what is this x we're dealing with here? This x was just nothing other than the mass we started with. Okay, we started with this mass, and therefore, this mass is 176, and the unit of mass we're going to use is the gram. So now, calculate the mass of oxygen gas initially present in the flask if the equilibrium constant at this temperature is that. So we then say it is 176 grams of oxygen. Okay, this one here is the end of this question from 2010. Is the end of this question here from 2010. Right. Any question now on this one? And then we're gonna just give a small homework that you can practice.
Question.
Okay, no question. All right. I know that you have kept here a little bit for some time. Okay, we're here for obviously just more than 2 hours now. But the rest of this have already been done. There's a question. This one. Okay, fertilizer company. So you can try this question about a fertilizer company, but I know that it's going to be very straightforward. Right, fertilizer company. So this fertilizer company is a question that it's you need to try and do. Let me see. Yeah, it is there part of your slide. So I'm just showing it here, but now you're gonna do this one. It is 7.4.1, 7.4.2, 7.4.3. Then it is 7.5. Then you drew 7.5. Right, and then now, yeah. Then you do the other one with the engineer. Then you do 7.6. Right. So in other words, you're gonna do 7.4.1, 7.4.2, 7.4.3, 7.5 during your own leisure time during the week. And then you can actually communicate that. Then you're gonna do 7.6 of the question about the fertilizer. Okay, this fertilizer company uses something we call the Haber process. Haber process. What is Haber process? Haber process is the industrial preparation of ammonia. Right, so this is it. Right, 7.6, that is your homework. So you're gonna do the 7.5.1, 7.5.2, 7.5.3, 7.5, and then you're gonna do 7.6. Right, it was awesome having a discussion with you now this day. Right, once again, we keep in touch during the week. Right, we're gonna do like several questions. Right, we're gonna do like several questions. The ones that are missing. Right, I want to make sure that we do like all of them. And
Okay.
okay, yeah, because we could not do all of them, but the ones that are missing, we're gonna do them during the week. We're gonna just discuss and see what time you can be free. Once again, you know, it can be late at night, 8 o'clock at night, 8 to 10. Normally, it works for some of the students, 8 o'clock at night, like 8 to 10, 2 hours. You can have that kind of a discussion. And do some of the questions that are missing. Yeah. But we thank you for joining us. And we have the little homework of the question 7. Yeah, this one we have on the screen. Right. Okay. We keep in touch then. Until next time, take care, Noah. And
Okay.
goodbye.
Thank you, sir.
Thanks,
Bye.
Noah. Goodbye, Noah. Bye.